So let me start again. So we're going to continue talking about transversality theorems from last time. So the main theorem of today is Thom transversality theorem. And it says that if you have two manifolds X and Y, and if you have a submanifold of the space of jets, and you consider the set of functions, smooth functions, whose kth jet is transverse to W, then this set is a residual subset of C infinity. So that means that there exists, that TW is the intersection of, it's a countable intersection of open and dense sets. Okay. Moreover, if W is closed, then TW is open. And of course, because we saw that C infinity is a bare space, since C infinity is bare, TW is dense. Okay. So that's the corollary that we want. So that in particular, we can always find a function whose kth jet is transverse to W, and they're everywhere. So they're in the neighborhood of anything. Okay, so if you have something that doesn't satisfy this transversality assumption, then you can just perturb it a little bit, and it will satisfy the transversality assumption. Okay, that's the idea. And this is kind of a heavy transversality assumption, but it'll be useful because you'll be able to apply this to a lot of cases. Okay, so let's start the proof. And the proof is a little bit technical, but it's not too much. It's just a little heavy in the notation. Okay, so so if I pick a sigma in W, so W is a jet, it lives in the jet space, so sigma is a jet. I want to define a neighborhood of sigma, but it's not an open neighborhood in the space of jets. This is a relatively open set. So it's going to be an open neighborhood in W. So, this is a relatively open set, which you can think of just the intersection of a genuine open neighborhood in the jet space with W. Okay, so, let me just draw a picture. So if this is W, and this is your sigma, then you're considering some open set like this. So it's open in W. Okay, so, but we're going to actually require some extra conditions on it. We're going to require that there are also charts phi sigma to Rn and psi sigma to Rm. So these are going to be charts around the source and the target of the jet. So charts around the source and the target, respectively. So the jet is the germ of a function from x to y, so the point x is alpha of sigma, and the image of the function is beta of sigma. I think you all remember that. Such that, well, the properties that I want are the following. So the first thing is I want the closure to be contained in W. Okay, so this is the closure in the total space. So I want a sequence of points here to have a closure in W. That's, yeah. And I want this guy to be compact. Okay, so this is pretty easy to do. When you look in a chart around sigma, it's easy to find this. I just am requiring that these open neighborhoods satisfy this. I also want the whole domain of the chart to be pre-compact. So U sigma bar to be compact. So you can always, shrink your chart to have this condition. So, and then you want, I also want to require that the source, if you take the source of everything in W sigma hat, that's contained in U sigma, and beta of W sigma hat is contained in V sigma. Okay, so you take a chart that's small enough, and that's possible because, because the jet space is a fiber bundle. So you can just choose that. Well, this condition, maybe let me draw a picture. So if this is your x times y, and here is your jet space, and you take a jet here, when you project it, you have something here. So if you take an open set here, you can choose a small enough neighborhood that projects here. Okay, so that's why this condition is easily, you can easily obtain something like this. And then the last condition is, I want to suppose, for simplicity, that the chart psi sigma is surjective. Okay, so psi sigma is a diffeomorphism. In general, when I think of a chart, I think of an embedding. So it's a diffeomorphism onto its image. I'm not necessarily supposing that it's a diffeomorphism onto the whole Euclidean space, but it's easy to find one. So if you have any chart, you can take a restriction to a ball, and the image will be a ball. Or you can take the pre-image of a ball centered around 0, and then you can take a diffeomorphism from this open ball to all of the Euclidean space. So this is very standard in manifolds. But if anyone has a question about why you can assume we can choose charts like that, please say it. Otherwise, I can keep going. Okay, so I choose charts like that. Which is an open set around each element of W, relatively open in W, and I choose charts like that satisfying these properties. And then, of course, W sigma, the collection of W sigma, is an open covering of W. So in the topology of W, this is an open covering. Of course, because they're open sets and they clearly cover all of W. So since this is true and W is second countable, because it's a submanifold of a second countable space, it follows that, well, we can take a countable subcovering. A countable subcover, which I'm going to call WJ. JNN. So now I have a countable subcover of relatively open sets of W, which satisfy these 4 properties. Okay, so these relatively open sets, they come with these charts. And now, let me do a quick definition. We say that a function is transverse to W on a closed set Wj bar if, actually on any set, but let's say on A, if F is transverse to W at X for every X in A. Okay, so that's actually true for any subset. This makes sense for any subset of no. Well, sorry. I'm going to write it like this. JK inverse for any subset of the domain here, of the target. So JK inverse of A. Or, sorry, to be even, it's even better. At the source. Okay. Okay. So that's kind of what you expect. So if you take a set here, you just say that you're transverse to W on the subset. If you are transverse everywhere, along this set, wherever this makes sense. So if you're transverse at X for every X in the set of sources of A. Okay, any questions? So now we can let Tj be the set of functions such that the kth jet of F yeah, sorry, this is a little silly. F is transverse to W. That's what happens when you change your notes. Let me write something that makes sense. So if G is a smooth function from X to Y, and W, this is a mini definition within the proof, and W is a submanifold of Y, and A is a subset, we say that F is transverse to W on A if G. If G is transverse to W at X for every X in the preimage of A. Okay. So that makes sense. Sorry, this is the definition. So now I want to consider basically another set that looks a lot like the original TW, but now I only want to require that the kth jet of F is transverse to W on Wj bar. Okay, so I only want the transversality condition to hold on Wj bar. Okay, so on the preimage of J bar, I want the transversality condition to hold. So because since the collection of Wj bars cover W, it follows that the set that I want, TW, so it's the set of functions whose kth jet is transverse to W everywhere, is just the intersection of all the TJs. Okay? So we need to show, so we want to show that TW is residual, so we need to show that TW or TJ is open and dense. Okay, so we'll show that for each J, TJ is open and dense. Any questions? Okay, so the first step is to show that TJ is open. Well, it basically follows from a proposition that we proved last time. So last time we proved the proposition. Well, this is a slightly modified proposition from last time, but if the proof is the same as last time. So the proposition was that if we have two manifolds, and you had a submanifold of Y, and say that you pick a subset which is closed in Y. So I pick a subset of W which is closed as in the topology of Y. Then this set of functions which are transverse to W on W tilde is open. Okay, so last time we proved this without this extra, we just assumed that W was equal to W prime. But if you look at the proof, we actually don't need that to be true at all. We just need it to be, we just need the transversality condition to hold on a closed set, on a closed subset. Okay, that's enough to guarantee that the set of the functions which are transverse is open. Okay, so last time we proved the proposition when W is equal to W prime, but the proof is the same. But the proof holds even when W prime, we never actually used the fact that W prime was equal to W. Okay, so since this is true, then now we can consider the set Tj tilde, which is the set of functions, smooth functions from X to the space of jets, such that J is transverse to W on Wj bar. Okay, so by this proposition, Tj tilde is open. And now we have the jet function. So the kth jet is a function from that takes a smooth function to the smooth functions from X to Jk to the jet space. Okay, and this function is continuous. I haven't proven that, but maybe I will leave it as an exercise if you haven't done it. I forget if I already asked about this as an exercise when we talked about jets, but about the CK topology. But if I haven't, this is a good exercise. So since this is a continuous function, then Tj, which is just the pre-image of Tj tilde by this map, is also open. Okay? And by the way, this is also the proof of the first fact, or of the second fact of the proposition, which is that if W is closed, then TW is open. So this will also imply this argument. This argument also implies that TW is open if W is closed. Okay, so the second part is already proven by the exact same argument. Okay. But the real interesting thing in the proposition is actually the second part, which is to show that these TJs are dense. Any questions about what I've said so far? No? You're still there. Are you still there?
We're still here.
Okay.
Yes.
Okay. So now is the interesting part, to show that this TJ is dense. And what we're actually going to do is we're going to be very explicit. So we're going to fix a function, a smooth function, and we will construct a sequence Gn, a sequence of smooth functions, such that Gn converges to F in the C-infinity topology, and Gn belongs to Tj. Okay, So that's what we need to show that Gn is that Tj is dense. Okay, so let's fix this F. Let's see how we construct Gn. So we will do that. Yeah, we'll construct Gn explicitly. So let phi and psi be the charts associated to Wj in its definition. So remember that we defined Wj together with two charts satisfying some conditions. Okay, so that just means that if Wj is W of some sigma, then we define phi to be phi of sigma, psi to be psi of sigma, and then U to be U of sigma, and V to be V of sigma. Okay, so that just means that this triple Wj, phi, and well, whatever, quintuple Wj, U, V, phi, and psi satisfy conditions A, B, C, D. Okay, so now we can actually perturb it by hand. So using these charts and using polynomials, we're going to perturb F in the following way. So first of all, I'm going to fix some bump functions. So fix smooth functions rho 1. So these are going to be bump functions. So they have rho 2 that goes from Rm to 0, 1. And they're going to have the property that rho 1 is identically 1 in a neighborhood of phi of the source of alpha of j bar, and the support of rho 1 is contained in phi of u. And the same thing for rho 2. So rho 2 is identically 1 in a neighborhood of phi of beta of the target, and the support of rho 2 is contained in psi of v. So, let me draw the picture again. If here is your manifold x times y, and here is your jet space, so it's your fiber bundle, you take some sigma here. Remember that what happened is I chose some Wj such that when you project it, that is going to be contained in the, so here is basically my u times v, and I chose it so that alpha of w bar times beta of wj bar is contained in u times v. Okay, so because this is these are open sets, and wj bar is compact, these are also closed. They are also compact, so they're going to be closed. So we can actually choose bump functions like this, which are one in the neighborhood of this closed set, but whose support is still contained in phi of u. And the same thing here. Okay? So let me...
Vinicius,
Oi.
you assume that the image of B under psi is all of our M. So can we just take rho 2 identically equal to 1?
Sorry, this is phi. Rho 2 is identically equal to 1? No. I wanted to have compact support. Sorry, I
Okay, so a compact support.
Yeah,
okay.
So maybe I should say that for rho 2. Yeah, because that's an empty statement. So the support of rho 2 is compact. I changed the proof from the book slightly. I think this is a little cleaner, but I forgot to change this part. Thanks. Who was that? Who talked? I didn't.
Miguel.
Miguel. Obrigado. I'm trying to get to know you, but it's a little hard. over the video. Okay. Okay, so now let B be the set of polynomial maps from Rn to Rm of degree less than or equal to k. Okay, now I can actually do the big definition. I mean, it's not that crazy, but the idea is now I want to use these charts and the bump functions to perturb my function f using polynomials. So how do I do that? Now you have all these elements, maybe it's not so hard to guess what you do. So what you do is you define a function gb, which will be equal to f of x if x is not in U, or f of x is not in V. So outside of this U and this V, if x is not in U, or if the image is not in V of f of x, then you define it like this. And then if you are in U and in V, if x is in U and f of x is in V, then you define it like this. So phi inverse of phi of f of x. So you basically look at the value of the function. Now this phi inverse is because now I'm going to do something in Rn. So I take my function, so sorry, psi inverse, and then I do psi of f of x. And then I sum the polynomial, but then I have to add a bump function. So I want to just sum b of phi of x. So b is a polynomial from Rn to Rm. So I have to take phi of x. But now I have to multiply by the bump function so that this thing actually is a well-defined function everywhere. So that it glues to the other thing. So I multiply this by rho 1 of phi of x. And then I multiply by rho 2 of psi of f of x. And I think I need one more parenthesis otherwise. Okay, so if I'm in U and in V, I have this expression. So this expression is a little ugly, but all that you're doing is you're taking your function f and you're adding a polynomial, but then you're putting these bump functions so that you're actually adding nothing near the boundary of the charts. And then outside these charts, you just have f of x. And notice that we assume that U bar was compact. So you're really only changing the function f on a compact set. Okay, so we can let g of x times b to y such that g of xb is gb of x. And exercise. It's not very hard, it's more of an exercise of notation and understanding the definition, is that G is smooth. Okay, so now we can let phi from x times b to jk of xy be the kth jet of GB. So phi of xb is the kth jet of GB. And it's simple to show once you know this. Maybe I don't even have to write exercise. Well, let me write it with a red arrow. This is the exercise color. Then phi is also smooth. Okay, so remember that if last time we showed a lemma, which is that if we had a function like that which was smooth, and if it was transverse to some submanifold here, then the set of parameters such that there was a lemma last time that said that if phi is smooth and phi is transverse to W, then for a dense set of B's, phi of dot B is also transverse to W. Okay, so then you would get this. And so you get this result, and then so since this would be true for a dense set of B's, then you know that phi of dot 0 is just the kth jet of f, because G0 is just f. And then you would find a function, a sequence Bn, which converges to 0. And it's easy to see that G of Bn converges to f in C infinity. And then you would actually have the property that Jk of Gbn is transverse to W for every n. Well, if this was true everywhere, then you would be done. But that's what the lemma was from last time. Okay, so of course it's not going to be so easy because we don't have the transversality condition everywhere. In TJ, we're actually, we restricted ourselves to a small situation in which we can control things. So we actually only want the transversality condition to hold on Wj bar. And in fact, this is not even going to be true everywhere in B. So the claim is a little bit weaker than this, but it's going to be good enough for the purposes of finding this. But at least on Wj bar, which is what we really want. So the claim is the following. There exists an open neighborhood of 0 . Actually, maybe I didn't emphasize this enough, but it's not hard to see that if the polynomial B is the 0 polynomial, then Gb is just identically equal to f. Okay, so what we're trying to do is find a sequence of polynomials Bn which converge to the 0th polynomial, such that Gbn is in Tj. Okay, so we claim that.
Question?
Yes, go ahead.
Why do you need to only change the function on a compact set?
Otherwise, the convergence is not going to be in the C infinity topology.
Okay.
Yeah, because remember that in CK, the convergence in CK is basically the same as saying that there exists a compact set, outside of which the function is equal. The sequence is equal to the function.
Okay.
Eventually.
Thank you.
Mm-hmm. Yeah, that's why we require this U here to be compact. Okay, so we claim that there exists an open neighborhood of 0 such that phi restricted to this guy. So along just on this open neighborhood, this is transverse to W on a neighborhood of Wj bar. So it's actually, we're going to actually prove that it's transverse more than just on Wj bar, but on a little neighborhood of Wj bar. So why is this claim enough? So this claim is enough because, so if we assume the claim, then I'm going to kind of redo this. Then we can apply the previous lemma, or the lemma from last class, to the pair phi restricted to x times b tilde, and my manifold now is just the intersection of W with this neighborhood of Wj bar. And this is a submanifold. This is a submanifold of jk of xy. Okay, because I'm just intersecting W with an open set. Okay, this is an open set in W, so this is going to be a submanifold of jk. And the lemma from last class is going to imply that there exists a sequence of polynomials in B tilde such that jk of gbn intersects this guy transversely, and bn goes to 0. So for any point, for example, 0, we can find a sequence like that. And this transversality condition, because this is a neighborhood, it implies that jk of gbn is transverse to W on wj bar. Okay, this is a very easy exercise. I mean, it's an exercise of writing down the definition. It's pretty trivial when you write things down. Okay. And since that's what I just said, but let me write it down. Since this GBN is identically equal to F outside U, it's easy to verify now that this converges in the same infinity topology to F. Because inside U, it's basically polynomial perturbations, and the polynomials are converging to 0. So the inside of U, you can look in charts, and this will converge with all its derivatives are going to converge uniformly. And outside of U, it's equal. Okay. So is this clear? Is it clear how the claim implies the theorem? Okay, so now I have to do the hard thing, which is to prove the claim. So we're going to actually choose, to choose the open neighborhood of 0, we're going to first fix a number, an epsilon. So it's a little, sometimes we do the proof, we prepare the proof before, so it seems a little funny, but it's okay, you'll see. So how do you do that? Well, first you let epsilon be half of the distance between psi of beta of wj bar and the pre-image of 0, 1. Okay, so let me explain one more time. So you take the set of sources, the set of targets of all the jets in wj bar. You look at the image under the chart. So this will give you some subset, some compact subset of Rm. And then you look at the distance between this set and the complement of the support. So if this is the support of row 2, this is contained here, and because we assume that row 2 was identically 1 in a neighborhood of this set, then that means that this distance is actually positive. Okay, I mean, this is the same as Rm. No, sorry, it's more than this. This is the set where row 2 is identically equal to 1. This is row 2, the inverse of 1. Okay. Okay, so now we can let B tilde be the set. Let me write it down here. Let B tilde be the set of polynomials B in B such that the norm of b of x is less than epsilon for every x in the support of rho 1. And here, when I pick this distance and this norm, you can choose whichever one you want in Rm. But I mean, you could just pick the Euclidean norm in Rn here, and you can pick the distance that's generated, the distance of sets just generated by this Euclidean norm in Rn. Doesn't matter too much which one you pick, but you have to pick one. Yeah, so this is much simpler than picking a metric on a manifold, for example. Okay, so it's clear that B tilde contains 0, and it's pretty obvious, I think, that B tilde is open. Okay, so if you pick a polynomial that's sufficiently close to 0, then it'll satisfy this condition as well. Okay, so now suppose that B is in B tilde and phi of xb is in Wj bar. Of course, if you pick xb whose image by phi is not in Wj bar, then Wj bar, then this condition is going to hold trivially. Okay? So actually, we're trying to show something slightly stronger. We were trying to show this is this is transverse to W on a neighborhood of a Wj prime, Wj bar. So I have to say maybe slightly more. But we're going to show something very, very strong. We will now show that phi is a local diffeomorphism near xb. So it implies that it's a local diffeomorphism near any point in the neighborhood of Wj bar. Okay? So this is actually going to be quite incredible, because if you're a local diffeomorphism, then that means you're transverse to anything. It doesn't matter what W is. You're going to be transverse to it. So in a way, like the essence of the proof, I would say that the core of the proof of this result is already in the lemma from last time. So you see that proving that it's a local diffeomorphism, then you basically don't care about W at all. So this also implies that phi will be transverse to anything. Okay, so let's see how we can transverse to anything at on a neighborhood on a neighborhood of Wj bar. Okay, so now let's see. Let's prove the statement. Any questions about this? Just is the logic clear here? Okay, so let's say you fix this xb in Wj prime, in Wj bar, and let's see what what gb of x is. So let me write it with the psi in front. So psi of jb of x is equal to psi of f of x plus rho 1 of phi of x, the two bump functions, rho 2 of psi of f of x times b of phi of x. Okay, so what do we know? we know that rho 1 is equal to 1 because x is in alpha of wj bar. And that's in the support. That's in the pre-image of 1. Of rho 1. So now we can write that this guy, the difference between GB and f of x in norm is going to be this guy is less than or equal to 1. Yeah, so this is going to be less than or equal to b of phi of x, which is less than epsilon. And so, by the definition of epsilon, this implies that rho of psi of f of x has to be equal to 1. Okay? So then that means that we can write psi of GB of x as psi of f of x. So at this point, we actually don't have the bump functions, plus b of phi of x, just like that. And the point is that this is true when I choose a phi b in the pre-image of wj bar. But it's also true, moreover, if x prime b prime is in x times b tilde, is sufficiently close to xb, I still have this condition because basically, because I'm still in the interior, even if the x is no longer in alpha of wj prime, but it's in a neighborhood of that, I assume that rho 1 was 1 is still in the neighborhood of alpha of wj bar. So even if it's sufficiently close, then I still get this equality here. So moreover, if this is sufficiently close, then we still get that psi of jb of x is equal to psi of x prime of b prime is equal to psi of f of x prime plus b prime of phi of x prime. Okay? So now, because looking at this equation, you can basically see that the function, we can rewrite, we can write phi of xb, x prime, b prime is going to be psi inverse of psi of f of x prime plus b prime of phi of x prime. 1, 2, 3. Okay, so I'm just perturbing by adding a polynomial like this, and it's actually like basically an easy exercise now to see that this is this has a local inverse. So phi has a local inverse. So phi is a map that goes from x times b tilde into the space of jets, the kth jets, and this has a local inverse. How is the local inverse given? So if you pick something, some jet, then we can let x prime be the source of the jet, and you can let b prime be the unique degree k polynomial which satisfies the fact that the kth jet that satisfies sigma equals to the kth jet of the function psi inverse of f composed with phi plus b composed with phi at the point x prime. B prime composed with phi at the point x prime. Okay. So you can tweak this a little bit, but this is a local statement, and it's just because of derivatives, what the kth jet is. Yeah. So anyway, maybe I can say that the exercise is to understand why there is always a unique such B prime. But I mean, basically, what you're doing here is you're looking at the kth jet in terms of charts, and then the kth jet of UV is just U times, it's bijective, is diffeomorphic to U times the set of polynomials of degree up to K. Okay, so that's basically the reason. But maybe if this was a little fast, I encourage you to think about filling the details. Okay, so this is the last thing that we needed to finish the proof. That's the end of the proof of the Thom transversality theorem. So let me just say it one more time. Let's go back with the argument. So we showed that this phi is a local diffeomorphism. So going back, that implies that phi is transverse to anything. I mean, on a neighborhood of this set over which we know it's a local diffeomorphism. And then using this fact, we can go back and use the lemma from last class to prove that for a dense set of parameters in V tilde, we have the transversality condition that we want. Okay, and then we can just take a sequence of parameters converging to 0. And that will give us the sequence of functions whose kth jet, which has a transversality condition we want on Wj bar, and that converge to f and c infinity. Okay, so that proves that Tj is a dense set, and we had also proven it's open. And Tw is the intersection, a countable intersection of sets of this form. Okay? All right, so that was a very long proof, maybe the most technical result of this course. So yeah, I'm happy to answer any questions before continuing. Are there any questions? Or is it clear, or is everybody confused?
Você poderia, tipo assim, elencar as ideias principais da prova do teorema, porque, não sei, parece um pouco confuso no final, mas quais foram os key steps, vamos dizer assim?
Okay, let me try to do the key steps. So the first step was to write W as sort of the union of closed subsets, Wj, countable closed subsets. And then we could write Tw as the intersection of Tj, where Tj was a set of functions that were transverse to W on one of these closed sets. I mean, compact sets, actually. Okay? And then the second step was to show Tj is open, and that was by the proposition from last class. That was not so hard, but it was the transversality really came in here. And the third step was to show Tj is dense. And we did it very explicitly using basically a result that, in a way, it's one of the classical transversality results, which is that if you have a family of maps that's transverse to some submanifold, then for a dense set of parameters, you get the transversality for the function. So this was done explicitly using a lemma from last class. Using the lemma from last class. Ok? Ajudou?
Ajudou sim. Obrigado.
De nada. Okay. All right. Maybe I can comment on this a little more. And what does it mean to do this explicitly? Well, because this is a compact set, we just perturbed f in a compact set using cutoffs of polynomials. And then we use the lemma to prove that there is a sequence of polynomials converging to 0, which have the transversality condition that we want on this compact set. Okay, yeah, maybe I should have said the key steps before the proof, but anyway, now you have both. You can watch the video and change the order if you want. Okay, so now let's move on to the corollaries. Unless someone has another question about the proof, we can go back. No? Okay, so the first corollary, which is really a corollary to the proof, doesn't follow from the statement, but let me say it anyway, is if you take two manifolds, X and Y, this corollary is useful sometimes. And you take a submanifold of the jet space, submanifolds, and you assume that the source of W, the source of the closure of W, is contained in some open set. Open set in X. Now let f be a certain function, and V be a neighborhood, open neighborhood. Then you can find, a function in this open neighborhood. So you can find a perturbation of f, basically, whose kth jet is transverse to W, and that's equal to f outside U. So in other words, if you have if you're requiring a transversality along some submanifold that is contained in U, or some submanifold of jets whose source is contained in some open set, then you can do the perturbation in such a way that you don't change the function outside this place where you require transversality. Okay, so I mean, maybe it's easier to understand if k is equal to 0. So if you just pick a subset, submanifold of the target. Yes. Yeah, if you have a submanifold image is contained in some U, so here is sort of use in the proof above, hello, I think my internet dropped. Hello?
Estamos ouvindo agora.
Vocês estão ouvindo? Tá.
Você poderia
Desculpa.
repetir a parte do desenho de novo, por favor?
Sim. Desculpa, pessoal. Aqui. Okay, so I don't know where it dropped. You didn't hear the proof at all, right?
Não, começou a travar na parte do desenho.
Ah, tá, desculpa. Então, okay, let me explain this again. So another way of understanding this corollary is, let's say you have a submanifold, and you look at the I'm just doing the picture for the case k equals 0. So you understand what's going on, but it's true for any k. If you take a submanifold in the target and you take the pre-image of the submanifold, outside of this pre-image, the transversality condition is vacuous. So you kind of don't care. And what this corollary is saying is that if you take an open set that contains the pre-image of W or W bar, to be more precise, then you can perturb F to make it transverse in such a way that you don't change F outside of this open set. So you only really need to perturb it in a neighborhood of the set of points where the transversality condition isn't vacuous. Okay? So that's what the corollary says. Okay, so how's the proof? So like I said, this is really a corollary to the proof. It doesn't follow from the statement. So the proof is, if you look at the proof of the Thom transversality theorem, for each sigma, remember we chose a W sigma, and we chose charts. So alpha, the source of W sigma bar is contained in U. So we might as well choose U sigma to also be contained in U. So we choose the domain of the chart small enough so it's contained in U. Okay. Well, let me write it like this. You choose U sigma such that alpha of W sigma bar is contained in U sigma and it's contained in U. Okay, and then since the perturbation that you do has a support in U sigma, then so for each B in B tilde, the chosen perturbation GB satisfies GB is equal to F outside U sigma, and hence outside of U. Okay, so this is true for every for every WJ. Say once you chose a countable subcollection, and you can actually go all the way to the intersection. So I'll leave you to fill in the details, but the core is this. It's not very hard once you understand the proof. Okay, so this is just a corollary to the proof, but now let's actually have some nice corollaries of the theorem. So I would say this is the elementary transversality theorem. It's basically the case k equals 0. I already alluded to that next time, but let me write it completely this time. So let's say you have X and Y manifolds. And now let's pick a submanifold of Y. So then the set of functions, of smooth functions, which are transverse to W, is dense in say infinity. Moreover, if W is closed, then this set is open. Okay, and the second condition has to do with what I was explaining before, the previous corollary. So if you take, say, two open sets, U1 and U2 open sets, such that U1 bar is contained in U2, and let F be a smooth function, and V be an open neighborhood. Then there exists a G smooth function such that G is equal to F in U1 and G is transverse to W outside U2. So if you're given yourself two open sets, then you can perturb. So that's in a way, like this perturbation is something that you can do locally. So you can make sure that F is still equal to G, that G is still equal to F here, but that it's transverse over here. So basically, you can make the transversality wherever you want without changing. You can perturb the function in a open set without changing the function on another open set that's far away from it. Okay, so that's B. So you can achieve transversality locally. That's kind of the moral.
Isn't it the other way around? G transverse to W inside of U1 and G equal F outside of U2? You keep the functions the same outside of the bigger open
It doesn't
set.
actually matter, but you could take the complement, but maybe I think it doesn't matter. You just have to switch U1 with U2, and you have to be careful with open and closed. But
no, because they're saying that G is equal to F in a compact set, and that G is transverse to W in an unbounded set, quote unquote unbounded set, potentially. Like, it's just.
I'm not saying either one is compact. I mean, I think that
It's just that from the other statement, you had a function equal to F outside of an open set, and now they are equal inside of the open set. That's all I'm saying. It feels like you changed the roles of the two things.
Yeah. Sorry, I see what you're saying. Maybe if you want, you can take the complement of U1 and the complement of U2. I have to think about just open and close. I'm not saying anything compact here. So if you just, the thing is, this condition here, G equals F, is a closed condition. So it's true in U1, it's true in the closure of U1. And the transversality condition is not quite closed. Yeah, anyway, let me write the proof and we can figure it out. Okay, first let's do the A. I mean, A is basically I left as an exercise last time, but you have to just look at the case k equals 0. So the zero jets from x to y, this is just x times y. And the zeroth jet function is just the graph. So, and it's clear that f is transverse to w if and only if the zeroth jet of f is transverse to x times w. I mean, that's all that you need to know. So then the set of functions, smooth functions, which are transverse to w, is the same as the set of functions whose zeroth jet is transverse to x times w. Okay. Well, for part B, I'm going to write the following. I'm going to write w bar, w tilde, is x times w minus the source of u2 bar. So that's contained in x times w. And then, that's what my w tilde is, and it's a closed. Yeah, it's a subset of x times w. And then I will apply, and it's clear that alpha of w tilde bar is contained in x minus u1 bar. So maybe if you're happier, maybe the picture that I drew is what's confusing you. If you want, you can write the picture like this. So this is u1. No, the green is u1, and the red is u2.
Okay, I think I get it now.
Okay. Yeah. So, yeah. Sorry. It's just maybe because we're looking at complements. That's slightly confusing, but yeah. So, by the corollary, now we can just apply the first corollary. There exists a G such that J0 of G is transverse to W prime, and G equals F on U1. So hence, J0 of G is transverse to X times W of U2. And therefore, as in the proof of A, because the zeroth jet is the same as basically x times y, and the zeroth jet of a function is just the graph, therefore J is transverse to W of U2, or outside of U2. So let's write outside of, like this preposition here. Okay. But by the way, is this equivalence here clear for everybody, or is anybody not sure about this equivalence? I can explain that. I left it as an exercise, but I can explain it. If nobody says anything, I won't explain it. Okay. Nobody said anything, so I'll keep going. Okay, so now we're going to talk about something that's even slightly more technical. Was anyone going to say something? I think someone unmuted.
Eu ia dizer uma coisa, professor.
Oi, fala.
Você poderia explicar a letra B de novo? Eu estou um pouco confuso ainda. Eu não estou entendendo quem que é o papel de V.
Então, V é só para dizer que em qualquer vizinhança de F, você consegue achar uma função que é transversal a W fora de U2 e é igual a F em 1. Basicamente,
Então G tem V, então.
Oi?
G tem V, então.
Ah, desculpa, eu esqueci de escrever. Yeah. That's what I wanted to say.
Ah, tá. Beleza.
Obrigado, Luciano.
É isso.
Isso. Yeah, I mean, in other words, this is just an explicit way to say that the set of G's that satisfy this condition that are equal to F in U1 and are transverse outside is still a dense set. Sorry, it's still a... Yeah, it's a dense set. It will intersect any open set, any non-empty open set. Okay, so now that we talked about all these technical things, we're going to talk about something even more technical, but in a little bit less detail, which is multi-jets. So let's talk about multi-jets. And I promise you the pain is coming to an end and the baby is going to be born. And then once we have the baby, we can do lots of good things with the baby. Multi-jets. So let's fix X and Y manifolds. And for a natural number, we'll define XS, which is basically I forget the name. Oh, this has a name, but maybe someone remembers the name. It's just a set of points in X to the S such that the points are always different. I think this has a name in algebraic geometry, but I forget the name. Okay, so it's like a some kind of set of points, but they cannot coincide. Okay, and then we can look at, basically we want to look at the jet space corresponding to something like this. So if alpha S is the product of the function alpha, so this is the source function that takes S jets to S points, we let the multi-jets, this is going to be the pre-image of this set XS. Okay, so that just means, it's the set of jets. This basically means you have S jets, each of which over a different point. Okay, that's what you have. And this is just a notation in a way. So the cool thing is that actually given a function, a smooth function, there's a section, and this of course is a bundle over XS parentheses. So given a function, you get a section of this bundle which is called the kth jet S. So it goes from xs to jks of xy. And this takes a multi-point x1, xs to the kth jet of f at x1 and the kth jet of f at xs. So this is just the way to kind of combine, to take derivatives, to take germs at functions at different points all at the same time. Okay, so I mean, yeah, so notice that xs is actually open. It's an open subset.
Is the order important?
Wait,
The order is important of the points?
no. Sorry, yes, I'm not modding out by the order. The order
Okay.
is yeah. I wouldn't say it's important, but it's there. Yeah, it's not a symmetric product.
Okay, okay.
Yeah.
Thank
If it was, then it wouldn't be an open subset of the product.
É tipo só o complementar da diagonal, não é?
Oi?
É o complementar da diagonal, não é?
Não, porque não é diagonal. É complementar do conjunto de pontos que tal que duas coordenadas coincidem, pelo menos. Ok?
Certo. Ah, sim.
Beleza? É mais complicado do que complementar da diagonal. A diagonal é uma coisa de dimensão 1. Isso aí é o complementar de alguma coisa de codimensão 1. Beleza?
Ok.
Okay. All right. So this guy's open. This JK, JSK is also an open subset of this space of jets. So it's also a manifold. Is open. So it is. So it's also a manifold. Okay, so now I can state the theorem. So this is the Thom transversality theorem for multi-jets. It says the following. So let X and Y be manifolds, and let W be a submanifold of the jet space, of the multi-jet space. Then the space TW, which is the space of functions, smooth functions, whose KS jet is transverse to W, is residual, and hence dense. Moreover, if W is compact, then TW is open. Okay? So this is the transversality theorem. Don't worry, I'm not going to prove it. Well, instead, I'm going to leave the proof as an exercise. The proof, is a little bit harder than the case for where basically S equals 1. But the idea is the same. It's not, there's nothing really new. I think stating the theorem is more interesting. I think the only thing that is kind of different here is that we're assuming that to get TW to be open, we need that W is compact. And the reason for that is basically because this manifold is not compact. Or it's not, it's not pre-compact with its topology. Sorry, this manifold is not compact either, but like you have sequences that converge in JK that do not converge here. This manifold is not closed. It's not a closed subset of. It's not a closed subset of JK. So when you actually look through the argument back, back there, and you pick a sequence of jets that converges to something, to another jet, if that jet is not in this JSK, then you won't be able to prove what you need to get the TWs still open. That's why you need this compactness. And maybe, I think it's worthwhile to do this exercise to understand this proof. But it's too boring to, I think, for me to try to do it again. But I think the point is that this transversality theorem for multi-jets is useful, and it'll be useful, for example, to prove the Whitney embedding theorem. Okay, so I think. Yeah, I think I'm going to stop here. We've already talked about a lot of things. So instead of starting a new topic, I'll stop here. And next time, we will see how we can get the Whitney immersion theorem and the Whitney embedding theorem from these transversality theorems.